Here we have three geometric series, and we're going to be taking a look at whether or not they converge or diverge, and then if they converge, we're going to be looking to find the sum. So we can remember for a geometric series, it was the sum starting at 1, and you're adding up a here multiplied by r to the power of n minus 1, which meant that the first term was going to be a, the second term was a times r, and then every time to go from one term to the next, we're just going to be multiplying by r. So it's just going to be a times r plus a times r squared, a times r to the 3, and so on. And now let's use that. Let's take a look at our first example. So when I'm looking at a geometric series, the one thing I want to know if I'm looking at whether or not it converges is what is the value of r, what is the common ratio. So we know that to get from one term to the next, we're going to multiply by r. So if I want to find out what r is, I can literally just look at the ratio of any two terms. I could take one term and divide it by the previous term to find r. So here we're going to take the easiest terms, are just sort of take the second term divided by the first term, do that ratio, and you will get r. So we need to know what is a2 and what is a1. Well, for us, a1, our first term is just 2, and our second term is going to be 3. So our common ratio is going to be 3 over 2. And we are interested in the absolute value of it, which doesn't matter for this one, but in general for a geometric series, we're looking at the absolute value of the common ratio. Our absolute value is 3 over 2, which is larger than 1, and therefore our geometric series is going to be divergent. Okay, and so for this one, that's it. That's all there is to it. We found the common ratio, but it is divergent, and we're done. So now let's take a look at the second example. So now let's take a look at number 2. And again, we start off by just finding that common ratio. Here, let's find a2. Let's find a1. A1 here is going to be 3 to the power of 1 minus 1, which will be 3 to the power of 0. So it's just 1 divided by 5 to the power of 2. And a2 will be 3 to the power of 1 divided by 5 to the power of 3. So we take these, we plug them in, and we do the ratio. So there's going to be just a little bit of algebra here as we simplify it. So we have this complex fraction. Let's rewrite it. 3 over 5 to the 3 multiplied by 5 squared. So we can simplify this fairly nicely. We end up with 3 divided by 5. That is our common ratio. So again, absolute value of r is 3 over 5, which is less than 1. And so this one is going to be convergent. And for a geometric series, if it is convergent, we should be able to find the sum. So here, that means our series 3 to the n minus 1 over 5 to the n plus 1 is going to be equal to a divided by 1 minus r. Okay, that's that value that we ended up with when we took our partial sum last time and we did the limit as the number of terms goes to infinity. When it was convergent, this limit gave us a divided by 1 minus r. So let's take that and plug in a, plug in r, except that we know what r is. R is 3 over 5, but we don't yet know what a is. So the nice thing about this is that every time for a geometric series, what is a? Well, if you look up here, a is always going to be the first term. That's it. On its own, a is the first term. So for us, what is a1? A1 is right here. It's 1 over 5 squared. So we can actually just simplify this, and let's see what we get when we simplify it. So 1 over 5 squared. Again, we're going to get here a complex fraction. So we have 1 over 5 squared. And it's going to be divided by, in this case, 2 over 5. But let's actually multiply here by 5 over 2. So we end up with 1 over 5 times 2. We end up with 1 over 10. And that's going to be what our value converges to. That's what our infinite series right here is equal to. So now let's take a look at the next one. Let's take a look at example 3. Here we do the same thing. R is A2 divided by A1. Let's find R2. Let's find R1. R2 is going to be 2 to the power of 4 multiplied by 3 to the power of 1 minus 2. So that'll be 3 to the power of minus 1. So it's actually just going to be 16 divided by 3. R1 will be 2 to the power of 2 multiplied by 3 to the power of 0. It's going to be just 4. So now we can plug those in. We get 16 divided by 3. And that's going to be divided by R1, which is just going to be 4. So now if we simplify this, what we end up getting is 4 divided by 3. That's our common ratio. Absolute value of R, 4 over 3, larger than 1, and therefore this series is divergent. So we don't need to find the sum because there is no sum. This one diverges. So this is how we're going to be working with geometric series. Okay, anytime you recognize that you have a geometric series, you're going to look to find what is the common ratio. The common ratio will always just be A2 divided by A1. So that's our common ratio is A2 over A1. And the second thing is, if your series actually converges, you will need to know what the value of A is. And A is always just going to be your first term in your series. And if it's convergent, we know it'll converge to A divided by 1 minus R. So that's how we work with it. We've seen geometric series, and we know how to find its sum if it converges. We've seen telescoping series, and we know how to find its sum if it converges. What we're going to be taking a look at now is actually going to be just some different tests. We're no longer going to be classifying our series, so to speak. What we're going to be doing is going through tests that we can apply to a series, and based on the result of that test, based on the output of that test, we will be able to tell, hopefully, whether the series is convergent or divergent. We won't know, unfortunately, what it converges to, but we will at least know that it is convergent.